Welcome. This is Team 12's presentation. My team is Jacob, Jay, Erica, that's me, Emmy, and Scott, and we did an analysis and redesign of a pet food extruder. So our product description, as I mentioned earlier, it's a pet food extruder, and it's used to create pet food pellets for pets. It can grind and mix different ingredients to create a final food mixture. It has a grinder, mixture, and extruder, and the anticipated product volume is 62,000 annual. Our exploded view for this first slide is actually just the structural components to reduce clutter. And on our second slide, we have the rest of the functional components, essentially all of the moving parts of the extruder itself. And our customer base, we decided that our primary customer would be pet food manufacturers. They'd probably have fleets of these machines in the factory and would all be fed with different food mixtures to produce their high variety, high volume outputs. And we thought that it would be good for custom food orders too, because it would have the same base, but you could just input different food mixtures as an input and you wouldn't have to change anything else. Our secondary customer would be animal shelters that decided to make their own pet food. This would include animal cafes or high-end breeding shelters, and those would probably be motivated to create customized food for their animals. But they could only be the shelters that had enough capital to buy the machine and the bulk food materials.
So moving on to the functional analysis of the extruder, the overall function is to make the food pellets. And we decided that the functions that make that up are that it must contain the food and the ingredients, grind the food, stir the food, must be able to move the food, and then press it and cut the food. And then in addition to that, secondary functions include remaining stable in order to ensure dependability and the ability to be repaired in order to assure convenience. Looking at the assembly sequences, our first sequence is a frame first top down sequence. So you assemble the frame from the top down, and then you attach all the components kind of one by one onto the frame, or maybe somewhat in parallel as it is supported, but it's mostly a frame first and then just put things one by one onto the frame. Assembly sequence 2 is a more parallel focused sequence. So you start building from the bottom of the frame, and then as you build up the frame, you attach the components onto it. So you put all of the components that are attached to the base on, then you put your vertical supports on and all the components that attach to the vertical supports, then the top and all the components that attach to the top, and then you're finished with the assembly. So the first sequence, because you're not having all your pieces attached to the frame as you're moving it around, it's easier to transfer and handle, and it's also easier to locate your parts because the frame is right there. But sequence 2 is, we decided would be easier for testing assemblies and assembling in parallel, because that's kind of the focus, is that everything gets put on side by side, and then you kind of just put it all together when you put the frame together. So we decided that overall sequence 2 was the superior sequence and is what we analyzed moving forward.
So moving on to our function component mapping matrix, as you can see here, all the frame parts and their main function is to remain stable. And then on our next slide here, we have all the other parts and they have all the other functions. Moving on, this is our bill of materials where we have our part names, quantities, materials, as well as different manufacturing and assembly processes, and our costs such as material, processing, assembly, and tooling. On the right-hand side, you can see the total cost per unit. Most of these parts are pretty cheap, besides the cutter blade here, because that needs to be manually machined. And then on the next slide, we have our extruder shaft, our gearbox, mixing drum, and our 2 motors, which are the significant costly components here. One of the reasons is that we are not factoring in the mass production cost for those. And then our total manufacturing cost for this is going to be $1,722, which is less than some prices we have seen on websites for pet food extruders. Moving on, we have our quad chart where we looked at each component and placed it in one of these 4 categories after analyzing their total cost and their functional importance.
And as you can see from our functional differential table, on the left-hand side, we have the functions that are the same for both consumer groups. And on the right-hand side, we have cut food, which is the only difference of the functions for different variations of the customer groups. You can see that all of the parts on the platform side are the parts that are shared between the two commonalities of all of the functional groups. And on the right-hand side, we have the extruder screen, which is related to the functional cut food, which is the only variance between the two products. On the left-hand side, we have the original, which is the small holes. And on the right-hand side, we have the variance, which gives a lot of variety to the high-end pet owners or pet cafes that would like the different option. And then for our modified assembly sequence, we moved the blade cover, extruder screen, cover fitting to the end of our assembly, which leads to delayed differentiation as shown in our second modified assembly sequence, as the first one has the midpoint being the choke point of being able to build and then waiting to determine which one we want, while in the second modified sequence, we can build all of our assembly up until the end cover.